Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the calculations of work and heat. Firstly, we should select the thermal system. The thermal system selected is a cylinder with a piston with a cross-sectional area of A, which contains 1 kilogram of gas. The force balance for the system is the gas in the system is in internal equilibrium. The force of the gas on the piston is balanced by the external force F and the friction force F between the piston and the cylinder wall. Details of the thermal system. Taking the gas in the cylinder together with the piston and cylinder as the thermal system, the friction between the piston and the cylinder is the internal friction. Assuming that the heat generated by the friction between the piston and the cylinder is completely absorbed by the gas in the cylinder, and the thermal state of the piston and the cylinder does not change, then the friction between the piston and the cylinder can be ignored during the analysis. Secondly, let's calculate the work. Let's calculate the work firstly with friction. Heat addition to the system is piston travel distance is the work is the expansion work subtracting the work loss and is expressed as the heat generated by the power loss due to the friction is called thermal production. The equality is also available to the compression process. During the compression process, if there is friction work loss, the surrounding will consume more work than the calculated value. But since delta W and PdV are both negative values at this time, the equality still holds. Let's then calculate the work without friction. And in this case, the work loss is 0. The work is the expansion work. Based on the expansion work, the technical work can be expressed as, for the process 1 to 2, the technical work is. Thirdly, let's calculate the heat. The calculation of heat is based on the entropy change for a process with confirmed paths and states of 1 and 2. The definition of entropy, equation 118, is for a process without friction and in equilibrium, the heat addition during the process is. Fourthly, let's see the diagram for work and heat. For a frictionless internal equilibrium process, the expansion work W and technical work WT can be expressed by the corresponding areas under the process curve and the left side of the pressure volume diagram. PV diagrams and calculations of the work are shown here. The heat addition in a reversible process can be expressed by the corresponding area under the process curve in the temperature entropy diagram. TS diagram and calculation for the heat are also shown here. Lastly, let's talk about the work and heat for a cycle. For a frictionless, internally balanced cycle, the expansion work is equal to the technical work. In the PV diagram, the expansion work can be represented by the area bounded by the cycle curve. The net heat addition for a cycle can be expressed by the area enclosed by the cycle curve in the TS diagram. The net heat addition of cycle is equal to the net work of that cycle. As is indicated, the net heat addition is equal to the net work output for a cycle. For internal unbalanced cycles with friction, although W0 and Q0 cannot be represented by the area enclosed by the cycle curve in PV diagram and the TS diagram, the above conclusion is still true. Okay, that's all for this task. Thank you very much and see you next time.